Hey, good afternoon. This is a presentation I made as part of my position as an undergraduate research assistant on the data visualization project I was working on this past semester. So in overview of the talk, we're going to first look at what I was given and what I gave out. Then we're going to talk about some of the classes and structures that I used, the pipeline, the input, processing, and output, and finally an interesting algorithm in there about how you position the nodes. So this is what I was given, these big walls of text, and what these are is output from the log files of the nodes. And so the research group I'm part of is doing high performance cloud computing, and so these are the worker nodes. And the worker nodes are virtual machines hosted in the cloud. And what's interesting about being a virtual machine is that we don't receive the whole computer. So that means we're sharing our computational resources. So sometimes the nodes will be really fast, and other times they'll be working slower because somebody else is doing something computationally expensive on the same core. And so that means that we need some sort of approach that will figure that out and distribute work intelligently. That way we can finish it in the shortest amount of time. And so what I was working on was the visualization of this process. And so this is what I'm given, these log files, and this is the output of that. So here we see all of our nodes in the network. They have their port number, and then they have the number of tasks in their queue. And so, kind of over time, we can see them chugging along. And they're all currently working right now, so they're all the same color, but you'll see some of them dim as they take a little short break. Here we see something interesting happen, so this node's red. And that means that it is working faster than the other nodes. And so, sort of interesting, so the algorithm should respond to that. But so this is just visualizing that speed differential. And so now, going to the next slide, let's look at some of the data structures I used to make this happen. And so one of the data structures was a script, and that was a list of chronologically ordered stage directions. And stage directions are just a very simple container class. They have a label, a start time, and an end time. And so the scripts just kind of look like stairs. So it's really easy to construct these when parsing the files. The files are chronological, so the scripts are chronological. Makes it very easy. It was easy to merge together different commands. So you parse out all of your bench in one spot, you parse out all your grow in another spot, and then you stick them together at the end. Very simple, kind of like merge sort, very easy meshing process. And then they were very easy to use for the node actors while performing, which we'll see here. So here we have our actors. They either represent a node or an edge, and they receive as input the script and the location, so where they should be and what they should be doing. And this is a generic representation of what a node actor looks like. It has its port number up at the top. It has its queue length, so the number of things it has on its plate, and then a benchmark speed. That's actually disabled for the one you saw just because it looked a little cluttered. And then all the actors have a perform function that takes the frame number. So if it's frame 10, you say, hey, show me what you look like at frame 10, or hey, show me what you look like at frame 12, or hey, show me what you look like at frame 14. And then it will draw that performance onto the image. And so this is the perform function. It's simple. We'll go through it. So if you don't have a script, just go ahead and draw a very basic version of yourself. But if you do have a script, go ahead and first make sure that there's nothing dead on top. Remove everything dead from the top. And then if you still have things, and it's time to start drawing the things, or time to start updating yourself in relationship to these commands, go ahead and go through every single command. And if you ever get a command that's won't have happened yet, you've reached the end of what you need to update for this current time step to be in step with what you should look like. And then you can go ahead and break. But if not, for every single one of these directions, go ahead and update your internal representation. So if it says do work, then hey, you should set yourself. You should know that you're going to be working. And then if you've received packages and your size has grown, then go ahead and set your size equal to whatever proper size it should be. And these will impact how it draws itself. But that was logic that you could just sort of imagine being included in self.drawSelf. And just sort of, this line represents the current time, and very simply you can think, okay, it hits work, and so it's gonna set working to true. Here, it hits work and it hits benchmark, so it's gonna set working equal to true, set its benchmark speed equal to 35. Here we're gonna get rid of those other two commands because their time has passed, and so now we're gonna say, okay, I'm gonna grow to be the size 8, and then I'm gonna keep working on now 32, task 32. So now let's go into the pipeline. I broke it down into input, process, and output. These aren't hard and fast, very clear distinctions, but sort of helpful to think about it. So for input, we receive the address of the log files, and so we can go ahead and parse out information from that. So we can parse out the graph structure, the port numbers, the node IDs, as well as form those scripts about the information we care about. When it's working, what its size is, how fast it's doing its work, things like that. Then we send that to Graph Animator, so for our processing. And this takes the graph and the port numbers and the scripts. And what it's going to do is it's going to figure out where all of our points should be, which is an interesting problem, which we'll come back to later. For now, you need to know it takes a graph and it's going to go ahead and give you some points that will sort of recreate how that graph looks. And then we build our edge actor. So for every single edge, you want an edge actor, and then build our node actors for every single node. You want to build a node actor. And then we go ahead and we animate. And the animation takes a start time, an end time, and a step size. And that's just going to say, call draw frame for every single frame that we want to, at the end we'll combine them together to make the final thing. So for every single time step, we call draw frame, which takes the frame, and then it goes through and asks every single actor to perform at that time. So every single edge, what do you look like at 10? Every single node, what do you look like at 10? Combines that together and saves the resulting image. Then you combine all of those guys into a GIF, and you can save. That's your final output. So let's talk about node positioning. This was kind of an interesting problem. So given a weighted graph, arrange the nodes so that latency is reflected in the distance between them. Basically, if point A and point B have really low latency, then they should be really close together. Or point A and point B have really large latency, well, they should be far apart from each other, just to kind of visually represent that in the final output. So the solution was a double nested for loop, looping through the same set of points. So point P and points. Then again, iterate through point Q and points, calculate the distance from P to Q, and then move Q along PQ so that you hit the distance you want. So if Q is too close, move it further away, and if Q is too far away, move it in, and just kind of over time, and you just iteratively do this. Like I have it set to maybe do 40 loops of this, and so slowly the nodes will sort of balance each other out and settle down into a happy spot. And then finally, I convert into browser coordinates. So sort of this algorithm is doing stuff in Cartesian coordinates, and the library we were using had the top left corner at 0, 0, and then the top right corner at 1000, 0. That's just a different way to do different way to do coordinates, which I call browser coordinates because it's very similar to how it's done for things like Flutter and other browser-based things. Neither here nor there. Just converted it, and then I go ahead and I declump the points. Sometimes they have really low latency between them, which is fine, but it just doesn't look good if they're 1 pixel and they're overlapping terribly. So just do this exact same algorithm, but instead of calculating the distance PQ, making sure that's equal to latency, instead you just say, hey, yeah, there's a minimum distance. And so, if you're too close, declump. So with that, we can sort of start to see something interesting. Well, all of our 1700s are kind of grouped together, and look, our 1400s grouped together. So we can, kind of have confidence that the way that we arranged these was the correct way to do it. And so we can see, oh well, this 12,000 is going to be far away from this 19,000, and so we expect a lot of latency between them. We can see some other interesting things like, oh well, this is weird. This node only has 1 task. It's keeping a very low number of tasks, whereas these nodes, they seem to have a lot of tasks. So something to look into, and can look, well, are these guys, receiving more tasks, and how's the algorithm responding to this, and get an idea of how's it respond whenever one of them goes cold. This guy's not working as fast anymore. So what do we expect to see here? And so it just gives a good way to look and visualize the data. So I appreciate you taking the time to watch this. I hope you found it interesting. Thank you.